Welcome to the Hammond Power Solutions presentation on selecting line reactors or drive isolation transformers for VFD applications. There are three main goals for this presentation. Number one, understand the physical differences between a reactor and a drive isolation transformer when used with variable frequency drives or VFDs. Number two, understand the application differences between a reactor and an isolation transformer. And three, be able to properly select a line reactor or drive isolation transformer based on your application's criteria. This is a typical three-phase iron core line reactor. It has 3 coils and an iron core. Unlike a transformer, which has a primary and secondary coil for each phase, a line reactor has just one coil and does not provide isolation or the ability to change voltages through winding ratios. While this appears to be a complicated picture, a reactor basically slows changes in currents. By smoothing out current flow, a reactor can help mitigate current harmonics and improve power quality on the line side of a VFD and can protect the VFD from voltage spikes. A load reactor between the VFD and the motor helps protect the motor from several issues, including the reflective wave phenomenon. This is a typical three-phase drive isolation transformer. With 3 sets of lugs and wires on the top and 4 sets of lugs and wires on the bottom of the unit, this is wired in a delta Y configuration with a neutral in the secondary. A line reactor does not have a neutral. Another major visual difference is the presence of voltage taps on the coils. By adjusting the taps, the user can fine-tune the voltage up or down in 1 to 4 increments, with each increment typically being 2.5% or 5%. A transformer is often used to change voltage. With drive isolation transformers, most configurations actually have the same input and output voltages, so the primary function is not to change voltage, but to provide electrical isolation between the primary and secondary coils. Transformers work by converting electricity into an electromagnetic field, which is another form of energy. The transformer's core conducts the electromagnetic field like a wire conducts electric current. The electromagnetic field then induces a current onto the secondary coil, which converts the electromagnetic field back into electricity and thus achieves isolation. The turns ratio between the primary and secondary coils determines the voltage. In addition to electrical isolation, a transformer like a reactor provides impedance, although unlike a reactor, a transformer also limits short circuit current. Let's begin the discussion on why a line reactor or a DIT is used in an application. As we discuss line reactors and drive isolation transformers, we will refer to this diagram several times. This represents a typical VFD with an arrangement for both line and load DITs and reactors. This is also wired in a classic 3-contactor bypass arrangement. When contactors 1 and 2 are closed, contactor 3 is open, and the motor is powered by the VFD with speed control. In bypass mode, contactor 3 is closed and contactors 1 and 2 are open to isolate the VFD, and the motor runs at full speed. The line and load reactors and DITs are never energized for across-the-line starts, since they are designed to work with VFDs and don't encounter the motor inrush currents, which happens with across-the-line start motors. Anything that rectifies AC to DC power is a nonlinear load and produces current harmonics. The line side of a VFD is basically a DC power supply, and it's a classic 3-phase nonlinear load with harmonic currents starting at the 5th harmonic, which is also 300 Hz on a 60 Hz system. Other large nonlinear loads can include heaters, arc furnaces, welders, and large DC power supplies and chargers. Overall, nonlinear loads now make up the large majority of utility loads. Nonlinear loads cause issues with the utilities, including power quality and higher line losses. Modern utility power meters increasingly allow utilities to monitor the added effects of nonlinear loads for individual users and allow utilities to charge penalties if a user exceeds harmonic values. The input or line side of a VFD uses rectifiers and is basically a DC power supply. This creates current harmonics when it transforms AC to DC power. As a result, the harmonics distort the utility's perfect red sine wave to make it look like the green wave. The VFD's input section also has sensors to monitor the incoming power and resultant DC bus voltage. Current harmonics can cause significant issues within a facility, and if they exceed a standard called IEEE 519, the utility can fine the user. The output of a VFD uses semiconductors to quickly switch the voltage on and off in a pulse width modulated or PWM output. By varying the width of the DC pulses, a VFD can simulate a wide range of frequencies from near 0 Hz to several hundred Hz and therefore control the speed of a motor. This PWM wave can have some unintended consequences, which can cause problems with cabling and the motor that we will discuss later. Line reactors and DITs are found on the line or input side of a VFD where it converts AC power to DC power. If line reactors and DITs are so good, why don't all VFDs have line reactors at the minimum, or all projects specify DITs? First, some manufacturers actually do have line reactors as a standard VFD component. Economics dictate that users may not see or understand the benefits of line reactors and DITs. As a result, they don't see a cost-benefit justification, just like safety is not the defining factor as to why everyone buys a car. For line reactors, manufacturers can't always determine which impedance is best. DITs are much larger and more costly than line reactors, sometimes even more costly than the VFD. While DITs are often but not always superior to line reactors, their higher cost and larger size often makes the cost-benefit ratio harder to justify. There are some situations where a line reactor or a DIT aren't just suggested but are really truly needed. First of all, if the facility is being fined for violating IEEE 19 standards by the utility, typically the user will ask for a solution, and depending on the severity, line reactors and DITs can provide harmonic mitigation. Reactors and DITs may be a solution or part of the solution. Reactors typically provide the least expensive method to remove harmonic currents. DITs cost more but are still competitive with other technologies for cost per amp of harmonic current removed. Number 2, a facility is being designed to meet IEEE 519 standards. Like number 1, reactors and DITs may be a solution or part of a solution. Number 3, a facility is being designed for meeting IEEE 519 standards and active harmonic filters are being used. Active harmonic filters, like our HPS True Wave, work like noise-canceling headphones. Instead of canceling audio waves with speakers, an active harmonic filter creates harmonics equal to but opposite of those created by the VFDs. Active harmonic filters benefit from each VFD having a line reactor at a minimum. Really, anytime you hear the words IEEE 519, you probably need to consider line reactors or DITs at a minimum. Number 4, if a customer expresses concern about power quality, then they really should have line reactors or DITs on their VFDs. This is a broad statement, but generally facilities such as hospitals, data centers, research centers, and industrial operations, which must have high degrees of uptime, are all concerned about power quality. And finally, number 5, VFDs can start to experience tripping events that are often the result of voltage spikes. This will often show up as an input or DC bus overvoltage fault. While people often associate line reactors with reducing current harmonics, another very important benefit is their ability to mitigate a variety of voltage disturbances, which can cause a drive to trip. This will often manifest itself as an input overvoltage or DC bus overvoltage. Vacuum breakers or vacuum contactors can cause large transient voltage spikes. Facilities such as data centers often test these components, sometimes daily. Switching power factor correction capacitors can also cause voltage spikes along with lightning. This issue should not be overstated. These types of voltage spikes occur very often and can cause many problems in facilities. DITs and line reactors, along with equipment such as SPDs and lightning arresters, can do a great job in mitigating these issues. Customers are often not concerned about power quality until they actually experience problems. If any of these problems are occurring within a facility, it may indicate line reactors or DITs are needed. Note that other issues can cause these problems, but adding line reactors or DITs is often one of the first solutions to be considered, especially if VFDs are a major power load. Internal facility harmonic issues can include transformer heating and losses, which can reduce the life of a transformer, incorrect meter, sensor, and communication data. Power factor correction capacitors can be damaged and fail. There can be nuisance tripping of circuit breakers and fuses caused by the addition of harmonic currents. And finally, a reduction in the life of electronic components that are usually such things as DC power supplies, which will often keep failing. Here are some general rules on when you need to consider a line reactor or a DIT. Backup generators have to be sized to supply not only the motor load, but the additional current harmonics. By reducing current harmonics, like line reactors and DITs, may reduce the load enough to allow the sizing of a smaller, less expensive generator. 240 volt open delta circuits are often associated with phase-to-phase voltage differences, which can cause current unbalance on the VFD's rectifier circuits. Note, phase unbalances can occur in any type of system configuration, but they are most prevalent in 240 volt open delta configurations, which are usually found in rural areas or older parts of electrical grid. Often an indication you have an open delta circuit is when there are two can-style transformers on the line feeding the system. If the system's total nonlinear load exceeds 25% of the system's total potential load, line reactors and DITs should be considered for each VFD. If transformers are heavily loaded above 75% for extended periods of time, harmonics can cause dangerous heating. Line reactors and DITs should be used to reduce this heating. DITs are inherently designed to be able to handle the extra heating caused by poor power quality in VFD-created harmonics. In this DIT and line reactor application, we are talking about protecting the larger power transformers that would feed the overall circuit and power a number of devices, including the VFDs. Generally, VFDs below 10 horsepower and sometimes larger don't have DC link chokes. The absence of a DC link choke means these VFDs put out more harmonics per amp of load than other VFDs, and should therefore be strongly considered for line reactors, especially for facilities like warehouses where you may have many smaller VFDs installed. This is an issue that not a lot of people are aware of. It is common that a VFD is powered by a transformer which is significantly larger than the VFD's individual load. A large transformer appears as a low impedance source to the VFD, which can cause overheating of the internal DC capacitor bank. As a rule of thumb, use a line reactor or DIT if the VFD doesn't have a DC link choke and the transformer supplying the drive has at least 10 times the current capacity of the VFD. If the VFD has a DC link choke, consider adding a line reactor or a DIT if the transformer's kVA or current rating is greater than 20 times the VFD's current rating. Example, the smallest distribution transformer is generally 15 kVA. 10% of 15 kVA is 1.5 kVA, which is roughly 2 horsepower. Since many VFDs below 10 horsepower don't have a DC link choke, and 15 kVA is typically the smallest distribution transformer, it's suggested that at the very least, VFDs 2 horsepower and below should have a line reactor. DITs, as we will learn, are often not practical for these smaller horsepower VFDs. By the same token, the most common distribution transformer is typically 5 times larger than 15 kVA at 75 kVA. This would indicate that in most cases, VFDs 10 horsepower and below will often benefit from having a DIT or line reactor. Let's start to examine individual issues for which line reactors and drive isolation transformers may be considered. As we look at each situation, we will explore the benefits of both solutions. Phase-to-phase input voltage imbalance. While VFDs can accept a wide range of voltage inputs, unbalanced three-phase voltages occur for several reasons. They are especially prevalent in older and rural electrical systems which use a three-phase open delta circuit, which uses 2 single-phase transformers instead of 1 three-phase transformer or a set of 3 single-phase transformers which are banked. Open delta circuits are also often ungrounded. Ungrounded circuits may also be found in mobile machinery and marine applications. If the phase-to-phase input voltages differ by more than 2%, this will cause unequal currents in the VFD, which can either damage components or cause nuisance tripping. Both line reactors and transformers can help mitigate the extra heating of VFD components that unequal voltages can cause. However, DITs have better performance and create a grounded Y neutral system on their secondary. While both can work, DITs are preferred when phase-to-phase input voltage imbalances are occurring. As we discussed previously, small VFDs often don't have DC link chokes. As a result, the smaller VFDs will produce more harmonic currents per motor amp than larger VFDs with DC link chokes. Applications with many small VFDs, like distribution centers with conveyors, can have significant harmonic current issues. Smaller VFDs are also more likely to be fed by transformers, which can supply 10, 20, or more times the load of the individual VFD. This makes the VFDs appear to be fed by a low impedance source and can cause capacitor heating and failure within the VFD. Reactors are used 1 per VFD and can usually be sized for the VFDs down to 1/2 horsepower. In addition, stock line reactors can be used to power this small percentage of VFDs which will employ a single-phase input. DITs typically don't go below 7.5 horsepower and do not come in single-phase configurations. As a result, due to performance, size, price, and availability, line reactors are preferred for smaller VFDs below 10 horsepower. Impedance performance. Impedance is an important consideration. The higher the impedance, the better the harmonic current mitigation. Reactors can be selected in 1.5, 3, or 5% configurations and can be wired in series for additional impedance configurations. DIT's impedance falls within a range of 3 to 6%. If a user wants a specific or minimum impedance, a custom and more expensive DIT may need to be sourced. DITs are historically oversized by kVA for the load, which means the actual impedance is lower than the nameplate. Here's an example. A 100 horsepower motor is about 75 kVA. A 100 horsepower VFD uses 118 kVA DIT, even though the load is only about 75 kVA. The nameplate, or percent Z, of the 118 kVA in this example is 5.2%. At 75% load, the percent Z or impedance is actually 3.3%. If the user wants 5%, a custom DIT may need to be sourced. Due to ease of selection, flexibility, and availability, reactors provide better impedance performance. Performance with an isolated ground. VFD manufacturers typically suggest that their units be supplied with an isolated ground. Systems such as delta and open delta systems may not have an isolated ground. Even neutral Y systems, especially in large facilities, may have questionable local ground quality. Reactors can provide either an isolated ground or a separately derived secondary. DITs provide true isolation between a VFD and the distribution system. A Y circuit with a grounded neutral can be created by a DIT secondary if only a delta system is available. Grounding the secondary Y neutral circuit also prevents the transformer of common mode transients from the transformer's primary to the VFD. As a result, transformers are preferred to provide a true isolated ground for a VFD. Let's talk about isolated grounds further. Here are some general rules on when you need a DIT instead of a line reactor. If the phase to ground voltage exceeds 125% of normal line to line voltage, or if you are using an ungrounded distribution system, or if you are using a 3-phase open delta system, especially with a single phase center tap high leg. An open delta system is pictured on the right. Here is a good visual to look for if you are trying to evaluate if you have an isolated ground. If the facility is being powered from a transformer setup that looks like the one on the left with just 2 transformers, there's a good chance that you're using an open delta system. If the facility is being powered by 3 separate transformers and one of those 3 cans is larger than the other 2, in this case all 3 cans are the same size, but if one of those 3 cans is larger, often you'll be powered by a star delta connection. These facilities are often found in older parts of the electrical grid. These configurations are often found in rural areas for farms, irrigation, water, wastewater, and golf courses. Anytime you see something like this on the pole powering your VFDs, You may need to investigate further and see if you have a delta or Y system. With ungrounded or floating ground delta systems, some issues can cause voltage swells. These comments would also include ungrounded or poorly grounded Y systems. Line to ground voltages can be up to the square root of 3 or 1.73 times the base voltage during faults. Voltage swells can be caused by sudden load decreases, such as when breakers and contactors operate or some forms of solid-state switching. In this case, voltage is equal to the change of impedance over the change of time. Voltage swells can also occur when large capacitor banks are switching. Note, large capacitor banks can be internal to your facility, but they might also include other nearby facilities or utility-owned capacitor banks. While this was taken from a Rockwell Automation manual, other VFD manufacturers have similar warnings. This says that grounding the transformer secondary is essential to the safety of personnel and the safe operation of the VFD. Leaving the secondary floating, and this can be caused unintentionally over time as grounds lose conductivity or are severed, can cause dangerous high voltages between the chassis of the drive and the internal power structure components. Exceeding the voltage rating of the input metal oxide varistor protection devices of your drive can also cause catastrophic failure. In all cases, the input power to the drive should be referenced to ground. This statement provides a powerful incentive to make sure that critical VFDs use a properly grounded system. A DIT offers a dedicated and usually much more local ground to a VFD than a general system can provide. Another nice benefit for using a dedicated drive isolation transformer for a VFD is the ability to ground out and remove common mode noise to ground. This circuit shows the path of the common mode noise to ground. Again, this is something that a line reactor will not be able to perform. In this case, we are going to quote Rockwell Automation, but other VFD manufacturers have made similar statements. Multiple VFDs that can have one or more internal references to ground on one transformer can produce a cumulative ground current that can trigger the ground fault interrupt circuit. With ungrounded distribution systems, the phase to ground MOV connection can become a continuous current path to ground. If you exceed the published phase to phase voltage, phase to ground voltage, or energy ratings, you can damage the MOV and cause the VFD to fault. Having each VFD on a drive isolation transformer eliminates this issue. Again, per Rockwell Automation, but this can be applied to other VFDs, suitable isolation is required for the drive when there is potential for abnormally high phase to ground voltages, which are in excess of 125% of the nominal line-to-line voltage. Suitable isolation is also required when the supply ground is tied to another system or equipment that can cause the ground potential to vary with operation. We recommend an isolation transformer when these conditions exist. Performance of harmonic cancellation, and note in this case we're talking about harmonic cancellation, not mitigation. Reactors and drive isolation transformers can mitigate and reduce current harmonics through their impedance. We have discussed previously where line reactors have better selection and availability of different impedances over DITs. Note that the higher the impedance, the better the current harmonic mitigation. However, if you have two standard 6-pulse VFDs of equal size or can group two sets of multiple VFDs into roughly equal loads, you can do a neat trick with DITs. You can order one set of DITs as standard delta Y with a normal 30 degrees phase shift, and a second set with a zigzag secondary that can give 0 degrees phase shift. This creates a kind of 12-pulse system that creates actual harmonic current cancellation at the larger transformer feeding these two phase-shifted transformers. A couple of caveats with a system like this. Performance will be better than a standard DIT or line reactor, but it will fall below that of a true 12-pulse VFD due to varying loads and differences in cable sizes and lengths of the loads. Line reactors and transformers can both mitigate harmonics, but only transformers can perform harmonic current cancellation. Cancellation occurs when a transformer is able to phase shift some of the harmonic currents being produced in one phase to another phase such that they cancel each other out. This is done with phase shifting or multi-pulse transformers. These transformers typically come in 12, 18, and 24 or higher pulse configurations. All standard VFDs have 3 sets of rectifiers, one for each phase. 12 pulse means that the transformer is fed with 3-phase power, but produces two separate offset sets of three-phase outputs. The VFD then needs 6 sets of rectifiers for a 12-pulse transformer. An 18-pulse transformer has 3 separate output coils, with each set of output coils being fed to a total of 9 rectifier sections on the 18-pulse VFD. By actually canceling out harmonic currents within the DIT's windings, better harmonic mitigation can be achieved than just with the reactor or base DIT. In fact, 18-pulse and higher DITs can often meet IEEE 519 distortion levels from when the VFD is considered the service entrance. While this isn't how IEEE was meant to be defined, it can be an effective technique to improve power quality within a facility. Here is an example of how to make a pseudo 12-pulse application using 2 VFDs or groups of VFDs with nearly identical loads. Half of the total load is fed with traditional delta-Y DITs at 30 degrees phase shift. The other half of the load is fed with DITs using either a delta-delta or delta to zigzag neutral secondary. Usually the zigzag option is preferred. This creates a pseudo 12-pulse configuration. Due to varied loads and differing impedances and cable lengths, this configuration will have lower cancellation rates than a true 12-pulse DIT, but can still provide better cancellation than either a standalone DIT or reactor. When using on a VFD output, if using a drive isolation transformer on a VFD output, you must know what the volts to hertz curve that the VFD will be using with the motor. This is especially true if the VFD will exceed 60 Hz, start at 50 Hz, or spend long times in low frequency situations where the VFD voltage boost is used to increase available torque at low speeds. Differing volts to Hertz curves can cause additional DIT heating and failure. DITs must always be custom made for any VFD output. Reactors aren't as sensitive to differing volts to Hertz curves, but it's always good to check the reactor with the manufacturer if the VFD will simulate output frequencies above 60 Hz. In this case, the advantage goes to the reactor. Voltages can change. With line reactors, there is always a voltage drop equivalent to the percent impedance at full load. Lower output voltages can mean lower voltages getting to both the VFD and the motor, which means less motor torque, higher currents, and more heat. Transformers can use their winding ratio to adjust voltages as needed. Taps can be used to adjust for localized low voltage conditions. There is no voltage drop with the transformer. Output voltages can be changed as needed. This gives the transformer the advantage. Users should remember that facilities are not always supplied with exactly the voltage needed, such as 480 or 600 volts. In both the US and Canada, range A is ideal and typical, but not always possible or practical. Range B voltages necessarily occur in practical design and operating conditions on the supply or user systems, or both. However, it should be recognized that because of conditions beyond the control of the supplier or user, or both, there will be infrequent and limited periods when sustained voltage is outside of even range B limits. Utilization equipment may not operate satisfactorily under these conditions, and protected devices may operate to protect the equipment. Again, only a transformer can react to situations like this. The National Electric Code allows for a 3% voltage drop in feeder circuits and another 3% voltage drop in branch circuits. This is on top of the voltage drop a line reactor can cause. The taps on a transformer can often accommodate for this and adjust the voltage back up. Even though reactors can cause voltage drops, it is still highly recommended in most cases where the voltage allows to install at a minimum a line reactor with a VFD. However, in this case, the advantage is still with the transformer. Physical size. As you can see by the chart, reactors are much smaller and lighter than the equivalent DIT. Line reactors can often be installed in a control enclosure, which can further protect them and allow easier wiring to the VFDs. Reactors, even while enclosed, have a large size and weight advantage over transformers. Installed cost. If reactors are smaller and lighter than transformers, they must use much less material and cost much less than the equivalent transformer. Reactors' small size and weight often means they are also easier and less expensive to install, giving reactors an advantage in overall installed cost. Efficiency and heat generation. Due to their small size, reactors have fewer losses than their much larger equivalent transformers. As a result, reactors generate less heat than the equivalent transformer. In this case, the advantage goes to the reactor. Ease of selection. Both transformers and reactors have their advantages. Reactors are more flexible to choose an impedance, while transformers can change the voltage and use taps to tune for local voltages. When the user understands how to initially select either a reactor or a transformer, the remaining steps to select a proper reactor or transformer part number is relatively easy. As a result, both reactors and transformers are tied for ease of selection. Short circuit withstand. During a short circuit fault, a transformer acts as a current limiting device. A transformer limits the maximum short circuit current to the inverse of the impedance times the full load amps. Example, if a transformer has 5% impedance and is rated for 100 amps, the inverse of 5% is 1 divided by 0.05, which equals 20. This transformer's maximum short circuit current would be 20 times 100 amps, or 2,000 amps. An iron core reactor, on the other hand, will have the core saturate during high currents found in short circuits. Upon saturation, the reactor basically operates as a wire and doesn't provide any current limiting. Therefore, transformers have an advantage when faced with a short circuit fault. Logistics. The logistical ability to get product quickly is important. Reactors are smaller and easier to transport. Reactors are typically stocked in North America to cover a number of popular voltages at either 3 or 5% impedance. Transformers are larger and can weigh 10 times or more than the equivalent reactor. They are typically only stocked in a 460 to 460 volt configuration, and other voltage configurations are typically made to order. Therefore, for their smaller size, weight, and wider stock base, reactors have a logistics advantage over transformers. Final comparison. In summary, reactors and transformers offer the user many advantages. Reactors can be used with smaller VFDs, have better impedance selection and performance. They can be used in a VFD output without derating. They are smaller and have a lower installed cost, and are easier to transport and generate less heat while energized than drive isolation transformers. Drive isolation transformers can create isolated grounds and help better with a variety of power distribution issues, such as unbalanced voltages. They can do actual harmonic cancellation, they can change the voltage as needed, have no voltage drop, and act as current limiting devices during short circuit faults. In most cases, the user must weigh the advantages of either a reactor or a transformer for their application. Both devices are a vital part of an overall VFD system. Properly selected, both devices can decrease VFD failures and tripping events to save the user time and money. Thank you for listening to Hammond's presentation. If you have any further questions, please visit our website at www.hammondpowersolutions.com or call us at any time. We'd be happy to work with you on any of your applications.